Hello everyone, and welcome to Office Hours with the Meter Environment team. Today's session will focus on soil water potential, and we're shooting for about 45 minutes of Q&A with our experts, Leo Rivera and Chris Chambers, whom I will introduce in just a moment. But before we start, we've got one housekeeping item. If you are watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your question on our website at metergroup.com. And then someone from our science and support team will get back to you with an answer via email. All right, with that out of the way, let's get started. Today, our panelists are research scientists and application specialists Leo Rivera and Chris Chambers. Leo Rivera operates as a research scientist and hydrology product manager at Meter Group. He earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also earned his master's degree in soil science. There he developed an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in Meter's hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. Chris Chambers operates as the support manager at Meter Group. He specializes in ecology and plant physiology and has over 13 years of experience helping researchers measure the soil-plant atmosphere continuum. So thanks for joining us, you guys. All right, let's get started taking our questions. And our first question of the day will be, what is the difference between soil moisture and soil water potential?
So they're both soil moisture, right?
Yep.
They both give you different pieces of information about your soil moisture.
Yeah.
So let's kind of break it out a little bit more and delineate them by water content and water potential.
Yep. Yeah. So water content tells us purely the amount of water that is there. Okay. It doesn't tell us anything about the availability of that water, whereas water potential
is your energy state. The differences in water potentials is going to determine which way the water in your soil is moving. So you really want to know both of these to have the complete water picture of your soil.
Yep.
So that you have the mass or the volume and also the energy state so that you know which way the water is going to move and how much energy has to be applied to move it.
Yeah, exactly. So it's an often used analogy is to temperature and heat content. And it's the energy state versus the amount, or the intensive versus extensive properties.
There you go again. So, I knew it would only take you. How far are we into this? We're like 2 minutes in, and he's got to bring out the intensive
versus extensive. And we have more resources about this on the website, but and if you want to dive deeper into it, but really it just boils down to how available is the water and how much water is there.
All right, next question. Which is the best sensor for measuring water potential lower than -1 atmosphere for research purposes?
Okay, so for those of you that aren't familiar with atmosphere as a unit of pressure.
It's -100?
Yeah, it's essentially
kPa?
Equal to -1 bar or -100 kilopascals. Okay. And in that case, anything between 0 and -100 kPa, the best sensor to make that measurement is a tensiometer.
Well, I mean, most of them cavitate close to or around -1
right
bar.
But if you need accuracy below that range,
that's right.
There's nothing that's going to beat the accuracy of a tensiometer.
You mean above that range?
Sorry, yes, above that range. Thank you. So anything above -100 kPa. Now some tensiometers can go beyond go lower than -100 kPa when they're degassed properly. We have
like the
HYPROP and the Teros 31.
Mm-hmm.
Those are all able to extend or delay that boiling phase. And
there's an asterisk there, though, right? You've got to get a really good fill.
Yeah, you have to get a good fill. Yeah, but ultimately, there's the best sensor is going to be the best accuracy in that range, and there's not really anything that can beat it.
No, not for accuracy.
Yeah.
But if you get much drier than that, then you're going to need something like the Teros 21, a matrix potential sensor that doesn't depend on the strength of the water column to take the measurement.
Exactly.
Okay, next one here. One of the most important equipment missing in irrigated agriculture is a reliable, reasonably priced tensiometer with pressure transducer. Is Meter Group working towards providing that to growers and researchers?
Do you agree with that statement?
I definitely agree that it's an important tool. I mean, there are other ways to get around it, which most people do right now. But I do think there's a lot of power in being able to have that measurement. I don't agree with the statement that there isn't an option available. The Teros 21 Gen 2 is a phenomenal option that is lower priced than a tensiometer.
It doesn't quite hit the tensiometer accuracy.
It doesn't.
But as far as a price point accuracy trade-off, it has a pretty strong value proposition.
Yeah, and I think for the purposes of irrigated ag and just trying to control your irrigation to stay within that range, I think its accuracy is well suited for that. It's not like we're trying to measure water movement in the capillary range.
Right.
It's really well suited for that. And we're working on a newer version too that's going to be easier to install and deinstall for irrigated ag purposes, where oftentimes we can't leave sensors in the ground. So there is more work going into this, but I do think there are great sensors on the market for measuring water potential in within the price range that is suitable for most irrigated ag.
Right. Great.
Our next question, when should you use a water potential sensor versus a water content sensor?
This sounds great. Let's have some fun with this one.
Okay.
Water balance, creating a water balance. Which sensor do you choose?
To get a water balance?
Yep.
Water content.
Water content.
Yep.
To know whether or not your plant is going to go into drought stress.
Water potential.
Water potential.
Yeah.
Okay. One for water content, one for water potential. What about, what if you're studying freeze thaw dynamics in soil? Stumper.
I mean, I guess it depends. If you're looking at freeze thaw dynamics, I mean, you're probably primarily just interested in water content, how much water is there. But there is some really interesting dynamics that happen due to the freezing and thawing action that creates this huge gradient in in water potential, because as soil freezes, it actually dries down the water potential really low. And so oftentimes when you go through these freeze thaw cycles, sometimes you'll notice that the ground the next day after a freeze thaw cycle looks like it's gotten really wet, but there's been no rain, right?
And the water potential may actually be giving
because
you the
the water
information
potential
there.
is driving that up. Now, having said all that, it's really hard to measure water potential when it's frozen.
Right.
But if you have temperature,
it can actually damage some of your equipment too.
Yeah, it can. But if you have temperature, you can actually determine based on how much it dropped below zero, what the water potential was. So that's kind of an interesting use case.
Okay, next one. Measuring soil health. So water content or water potential?
I'm going to want both.
Both, exactly.
Yeah.
I vote for both too.
Yeah, because you need to know especially in situ, if you can characterize the moisture release curve, the way you're impacting soil health is going to have a big effect on that. On that characteristic curve.
Right, exactly.
All right. This one is asking, for the tensiometer, if you are looking to measure potential at a specific root depth, how do you know what depth to install the sensor with a long water column?
So this is kind of referring to older style tensiometers that have long water columns in them.
Yeah, most of our tensiometers, except for the Teros 31, have constant water columns, right?
Yep, very small water columns only held within the ceramic.
Yep. So for your field ones, that we've kind of moved beyond that question. And if you have a long water column like the Teros 31, you can compensate for it.
Yeah. So it's a pretty simple correction. It's just based on the height, gravitational height. So if you install it at an angle, you need to know what your gravitational height of the water column is, not the total length of the water column.
Right.
But the beautiful thing is that most newer tensiometers, you don't really have to worry about this for the field. We don't typically use the tensiometer like the Teros 31 in the field because it's just not as well suited for that, and we have better tools.
That's right. Teros 32 is going to be a better option, and this isn't a problem.
Yeah, exactly.
Or a Teros 21. It's like getting my numbers mixed up.
Yeah.
There. The Teros 21 is an option as well that where this isn't a problem.
Yep. Yeah. So most new stuff, don't really have to worry about it. If you do have a traditional tensiometer, it's just some basic math to make the correction.
Or it may be time for an upgrade.
Exactly.
This next person asks, what sensor might be appropriate in more arid environments when the soil water potential might be very low for most of the year?
This is kind of a tricky one to get into. Tensiometer's out of the question, you can assume.
Yep.
So a Terrace 21 is going to be a good option. We're getting pretty good accuracies down to permanent wilting point and beyond.
Yep.
And what else? Heat dissipation sensor would probably be a good call if you have the patience to calibrate them.
Exactly. Yep. So no, I think that's the right call there is your non-maintenance type water potential sensors that give you the accuracy that you need in that range. And right now, the only ones that I know of are that work well is something like the Terrace 21 or the heat dissipation sensor. Beyond that,
unless you're going to take samples and run them in a WP4C, in which case you lose the temporal variability or the temporal resolution in your data.
Yeah. Yeah. Beyond that, I would probably also want to measure water content along with that, just because I think you might get a little more information.
It's a little more sensitive at the drier range, and you could generate a soil water retention curve and actually approach the problem that way.
Yeah.
Our next question is, can the relationship between soil moisture and water potential in the range of accuracy of the water potential sensor be used to infer water potential from soil moisture readings in drier conditions?
Yeah, absolutely. I mean, this is what people do. We use the soil moisture release curve all the time to make this correlation. I personally, I don't hate it, but you need to understand some of the potential drawbacks of this approach.
Now, how much does hysteresis play in this range?
Exactly.
Like when you get to this area, it's soil dependent, right?
It is. It's soil dependent, and hysteresis can play a big impact whether you're on the wetting or drying cycle. Okay. And then in between that, the scanning curve, where you're going between these wetting and drying cycles within that hysteresis band, you're going to get differences. So you just need to know that there's going to be potential errors in your water potential estimate because of hysteresis and because of what are you using, a lab-based dry down curve, a lab-based wetting curve. There will be some potential error because of that. Now,
and most of the time we're going to be interested in the drying curve, right? Because your wetting curve is generally really rapid.
Yeah, typically that's correct. And that's what I would use.
If you had to pick just one, instead of a sophisticated analysis.
Yeah, I would use a drying curve.
Yep.
Just know that there are some drawbacks there that come with that. And so as long as you understand that, then I think it's safe to use this approach.
Great.
Okay, this one says, are there effects from digging a trench on the soil at the site?
This is kind of disappointingly not clear to me. I feel like we should have a better handle on this.
Yeah, I think that it depends. I mean, well, there certainly can be, because when you're digging a trench, it's a pretty large disturbance to the site. And depending on if you're on the uphill or down, especially if you're on a slope, say you dig a trench uphill from where you're installing the sensors, you're going to alter the hydraulic properties of that soil.
Even on the downhill, though, you're probably going to have an effect.
You are, but I'd rather have my trench on the downhill side. I mean, if you have to pick between the two, having your trench on the downhill side minimizes the impact on water movement in that.
Where gravitational water is going to wind up near your sensors.
Exactly. Yeah. The other thing is when you put the soil back into the pit, there's two things that I always try to do as best as possible, and put it back in the same layer, same arrangement that you pulled it out.
Great advice.
Pack in layers to try and get as best as you can to the original bulk density of the soil. You're not going to be perfect. It's really hard to get that back to the exact same bulk density. Sure. Never leave a depression on the site. If you dig a trench and then you have a depression there, or even if you've gotten it packed flat, there's a good chance that over time it's going to form a depression.
Right.
So you want to make sure that you have a little bit of a mound of soil on there to allow for that settling that we know is going to happen. And try to avoid that. Or if you can, use different tools like our borehole installation tool, which minimizes the site impact. then that really can help as well.
That's right. You're disturbing less of the vegetation. You're disturbing less of the soil structure. Basically, just keeping your site closer to the condition that you would like to study.
Yeah. So if you can minimize site impact, it's always
a good idea.
Yeah.
Our next question asks, are there case studies for plants and turf available?
Yep. So we have a couple case studies that we've done and published, working with some researchers at BYU, Brian Hopkins, and Neil Hansen, doing some work in turf and also a case study on potatoes. So there are quite a few of those available, but there are plenty of other researchers that have done some of this work. And also one of the best things to look at is some of the papers from Sterling Taylor, where he has some of these water potential ranges published. So yeah, there's quite a few out there, and you can look on our site and look at some of the case studies we have available, or dig deeper into the literature.
There's lots of instances in the literature of water potentials at which plants, different species, different soils are happy.
Yep.
All right. This one is asking, are sensors available that measure at 2 inches and 5 inches at the same time to better know how the soil water potential is changing in the soil profile?
Soil profile's pretty important to know what's happening in there for a lot of questions. There are some profile probes available, not so much for water potential or matrix potential, though.
Not for water potential. And that's definitely it's on the list of things that would be really nice to make. And maybe one day we'll make one down the road, or somebody else will. We'll see.
Yeah.
It's not an easy thing to make. So right now your best approach is just to install your sensors at the depths that you need to monitor. But yeah, I do absolutely agree. Understanding profile dynamics is really important. But there's no profile sensor for matrix potential available.
That's right.
Yeah, we have released the Teros 54, which is our new profile soil moisture sensor
for water content.
Yep. And so that is our first stab at a profile sensor that we're pretty excited about. But depending on what depths you want to measure at, sometimes you're better off just doing an individual sensor, especially if you have very specific depths that you want to measure at.
That's right.
This one says, how can you measure capillary water potential?
It's a really good question.
Take a step back and define that for us.
So capillary water potential has to do with the actual pores in the soil pulling the water up, acting like capillaries.
And different size capillaries have a larger effect, right?
Exactly. So it depends on the pore size distribution of your soil, what that looks like. However, the capillary range that we typically define in soil water potential is 0 to 100, minus 100 kPa.
Okay.
So you're ultimately measuring multiple things. You're not just measuring the capillary water potential, but if we know that that's the capillary range, then we can look at the water potential changes within 0 to minus 100 kPa and know that those changes are primarily due to changes in the capillary range.
Do you generally want to know something about your soil structure in this case? Because it's largely a function of structure, is it not?
Oh, it absolutely is a function of structure. It's a function of structure and pore size distribution. Well, pore size distribution.
So that's the most important variable.
Yeah.
If you really want to nail this down.
Yeah. But if you're measuring within that range, then you'll know that that is all capillary water that's changing. When you get beyond that, then we get into the adsorbed film range. And then beyond that, we get into the really inner layer changes of water potential. And those are really low water potentials.
Right.
And the only people that are interested in that are going to be geotechnical engineers or soil mineralogists, things like that. But yeah, measuring within the 0 to minus 100 kPa range gives you the information you need to know about changes in capillary water.
All right. This question is asking, how do sodium and bicarbonates in water affect tensiometer readings?
So mostly tensiometers are going to ignore solutes in the soil.
Yeah.
Right. The ceramic is going to let them diffuse in and out. So there's no potential difference.
Yeah.
It's going to equilibrate and it shouldn't really matter. Depending on the method you're using. So for tensiometers, it's you probably won't see anything. The Teros, something like the Teros 21 that actually measures water content. If you get a high enough salt level, then that's going to mess with the water content reading. Yep. And since we infer the matrix potential from a water content, then you can run into problems. So this is kind of sensor dependent. Tensiometers generally aren't going to worry about solutes in the soil, but pay attention to the base measurement of some of your other sensors out there.
Yeah. And Chris, your chemistry is probably a little bit stronger than mine is. Okay. Bicarbonates, yes. Do we worry about those precipitating out?
That really depends. Mm-hmm. This is pH dependent, I believe. So it kind of depends on what else is happening in your soil.
Yeah.
If everything's in equilibrium, probably don't have to worry about it. But things in soil change. So it's always good to know what's happening in your soil.
Our next question is, how sensitive is a tensiometer? If we install it in one place and the pressure changes, say to only 1 millimeter, can we measure it?
If you want to get the best possible resolution, the tensiometer is the way to go.
Yep.
What is the resolution of the Teros 31?
I believe it is.
It's 5.
On a ZL6 is well, you can resolve, I think, to 0.1 hectopascal.
Ooh, cool.
Which is about 1 millimeter. Approximately of changes in water potential. So I'd say for them, that 1 millimeter change is pretty dang precise. I don't know if we're going to be as accurate because our accuracy is about plus or minus half a kilopascal.
Okay.
But the resolution is 0.1. So we can definitely see those changes. It's not going to be as accurate. Now we are working on a project with, some researchers at Utah State where they're trying to deploy these on a space station project.
Nice.
And they are looking for much higher precision, and it is absolutely doable. The pressure transducers on those tensiometers have really high resolution when used on third-party systems like a Chemical Scientific data logger.
Right.
And so we're working with them to actually utilize that system to give them the resolution that they need.
So the reader has part to play in the pressure transducer,
absolutely.
Sensitivity.
Yeah.
Great.
So we can definitely see that. Most people don't need that type of resolution, except in some of these niche cases.
Studying plants and water movement in space just sounds fun.
Yeah. Yeah. And I'm excited to see how that one turns out.
This next person is asking, what is the physical meaning of a positive result from a tensiometer?
That is a great question. So typically, if we see a positive reading on a tensiometer, that means we're saturated, right?
And then some.
Yeah, and then some. And so the more positive that reading goes, that indicates that we have a higher water column above the tensiometer. So oftentimes, this is really the beauty in tensiometers, is especially if you're doing, let's say, for example, you're studying slope stability, where when you see these positive pore pressures, which is what they typically refer to it, that's a bad thing.
Right.
Or that indicates a higher risk of a slope failure. And so they use tensiometers in these cases to look when the pore pressure is negative, as it's typically referred to as by geotechs, or when we have normal water potentials. And then when it goes positive, we look at those readings and are treating the tensiometers like a piezometer, which is a tool that we use to measure water levels,
right?
In the saturated zone. So this is a really cool thing about tensiometers, is they can give us information in saturated conditions as well.
Yep.
It's not a error or anything with the tensiometer. That's just a normal reading, and you've just got a positive water column above the sensor.
That's right. And it is unique to tensiometers. If your Teros 21 gives you a positive reading, give me a call.
All right. This one is asking, are sensors available that measure at 2 inches and 5 inches at the same time to better know how the soil water potential is changing in the soil profile?
So, talking about soil water retention curves here.
Yep.
And so what do you think is most interesting about soil water retention curves? Like, it's neat, it's cool. It's like, here, look, we can do this with the Teros 21 and the Teros 12. Why is that so important?
Yeah. So yeah, there absolutely is this relationship, and it's important because it tells us a lot about the soil properties. We can go really deep, we could do deep dive into all the information that you can get out of a soil moisture release curve, because there's actually quite a bit, from shrink swell capacity of soils to soil specific surface area. Now that's diving really deep and maybe not what we need to do for this, but ultimately it just tells us we often refer to this as the fingerprint of the soil, right? Because depending on changes in bulk density, changes in organic matter, structural changes in the soil, these all impact that moisture release curve.
Right.
And we need to understand that to understand, one, how much water can be stored in the soil, how much water is available for plants, what else? I mean, there's just so much information that you can get out of that release curve.
If you have the soil water retention curve, do you even really need to know like the soil texture? Or do you still want to have that information?
Oh, you're still going to want to have that information, because again, there's so many factors that impact. It's not just texture on its own that impacts.
The more that you can account for in your analysis, the better.
Yeah, exactly. Okay. So it's great. And measuring it in situ is really is an ideal way to do it if you can. It's still hard to do, but it's more doable now with the sensors that we have available. It's sometimes hard to compare lab-based retention curves with the field-based soil moisture release curves. I think Colin is going to present on one in his webinar, and so we'll see how that comes out. And we've seen some people doing that. But
is that mostly because of the control of the process, or the completion, or how complete the curve is? Because in the field, you're only going to get a partial curve most of the time.
Exactly. It has some of it has to do with the dynamics in the field, because you're going through the scanning curves. So you're going through those frequent wetting and drying curves. Also, if your lab curve isn't based on an intact core sample, you're going to have differences due to just the fact that the sample really isn't the exact same as what's in the field.
Right.
So things like that can impact it. Yeah. And also, it's very rare that you truly get fully saturated in the field.
Right.
Whereas,
you always got some air trapped somewhere.
Yeah, exactly. Yeah. And whereas with the lab-based retention curve, we completely saturate that soil sample. So you'll see differences in the actual max water content that you hit with the lab-based curve. So there's just things like that.
All right. This question, the only option for container media is a tensiometer, isn't it?
In my experience, I agree with that statement. The Teros 21, I've had some really bad situations for my plants trying to use a Teros 21 in container medium personally. The installation is tricky. It's hard to tell exactly the full extent of the problems with something like the Teros 21. But the tensiometer is just precise enough and responsive enough that you can get good information from it. In most media, something you need to watch out for in container media is the shape of the soil water retention curve.
Yeah.
It's like everything looks great for matrix potential for a long time, but there's a cliff that it's waiting to fall off of if it gets dry enough. So if you're not paying attention to it, if you're not getting your notifications, and you go just a little bit too far, you're going to have a small change in water content that drives off the cliff, and there's no water left for your plants, basically.
Yeah. No, I have to agree with that. I mean, when you actually want to measure water potentials in most of these soilless medias, they're used in containers. The tensiometer is the best option. I will say there's a caveat to that we did a study with a researcher at University of Georgia. This was like almost 10 years ago now, where we were seeing plants that were stressing at minus 10 kPa.
Oh man.
So water potential only tells you part of the story. And what we found with those is that it was actually a limitation due to hydraulic conductivity. And so technically the water potential where we were measuring was minus 10 kPa, or what you would assume is to be around minus 10 kPa, but right around the surfaces of the root, because there's less redistribution of water, or slower redistribution of water, the plant was starting to stress due to the limited unsaturated hydraulic conductivity. So it is something you have to be careful with and know what the optimal water potential ranges to stay within for that media are.
And in that case, something like your water content sensor, which samples a larger section of soil, you don't have to worry about something like that.
Yeah, exactly. So yeah, soilless medias can be a little tricky sometimes.
Yep.
This next person is asking, we have a HYPROP and WP4C. What challenges can we expect with analyzing high clay vertisol soils?
It's mostly the shrink swell thing, right?
That's the biggest factor, is the shrink swell of the soil. None of these methods really handle that all that well, especially as you get it really dry. You get large cracks that form, and it shrinks away from the edge of the rings on the HYPROP.
But not just that, you can lose contact with your tensiometers too.
Yeah. Yep. So yeah, these vertisols are tricky. I think for the most part within the range of the HYPROP, I wouldn't push it beyond the minus 100 kPa range. If you try to go lower and use like their air entry point, you're really going to get that shrinkage that's occurring.
But the WP4C is a little robust to that, right?
Yeah. So that's where I would just use the very wet end for the for the HYPROP, and then just jump over to the WP4C.
More points than the WP4C once you get past that.
Yeah.
Once you get past that wet range that the WP4C doesn't do very well, you should be in good shape.
Yeah. And the WP4C does great with these soils. And we use that same technology on the VSA as well to characterize these soils. And these are the types of soils where there's actually a lot of information in that dry end of the soil moisture release curve, especially when we look at the hysteresis that occurs down there too. So it's they're really interesting to look at. You just need to understand some of the limitations and how you are going to approach those measurements.
Right.
This next question asks, how do you develop a soil moisture release curve in highly variable soils?
Sample.
Yeah. I mean, it's if they're highly variable soils, you need to collect samples to represent that variability.
And if you get a handle on the spatial variability of your soil types, then you're in good shape.
Yeah. Yeah. Now, some people might try to use pedotransfer functions, which are tools that we use where they pull in a large database of soils, and then you input some of these different changes in variability. Maybe it's texture, maybe it's bulk density, and you can try to use those to kind of characterize some of those changes, but they're not perfect. The best thing to do is just sample that variability.
I'm sure AI will open that up at some point once the database is fully ingested.
We'll have a soil.gp or soil GPT at some point. No, it's really, I mean, this is something that we deal with in all types of measurements, not just soil moisture release curves, hydraulic conductivity, even just changes in soil moisture spatially. Really, the best way to approach this is through sampling, but also characterizing where that variability in the field is coming from. And there are tools that we can use to help with that.
If in doubt, buy more HYPROPs and return more samples.
Yep. But just characterize where that variability is going to come from and take your samples from within those zones to try and characterize it as best as you can.
All right, we're getting near the end, so we'll do a couple more questions here. This one is asking, how is the temperature sensitivity of a water potential sensor? Are there any compensation equations for those sensors?
So the water potential is temperature. There is a temperature effect, right?
Exactly. So water potential is temperature dependent. There's also the potential for sensor sensitivity,
right,
to this. I know that's something we spent a lot of time on the Teros 21 Gen 2 to try and limit that temperature sensitivity,
right,
or the sensor temperature sensitivity. But there is still water potential. That's water potential. Just it changes with temperature. So some of those are just actual changes in water potential.
So it's going to be pretty small in a tensiometer.
Yep.
Where you're doing a much more direct measurement.
Exactly.
And in the ones that measure indirect measurements, that make indirect measurements like the Teros 21, then you're going to have to be more careful of, well, how does temperature affect what the Teros 21 is measuring?
Yep.
And also, like the Teros 21 relies on a soil water retention curve. And so if you get to a part of the curve where a small change in water content, say from a temperature change, results in a large change in matrix potential, then you're going to get noisier data.
Yep. Yeah. And we've seen some papers published on doing some of these corrections with the Teros 21. I can't remember where this group was out of that published one. Was it either Swiss or out of Italy? But we have some of those papers linked in the on our literature sources on the website.
Right.
Really, I think most of the sensitivity comes in on the dry range, right?
Exactly.
It's not as important on the wet. Even for the Terrace 21, it's not as big a deal on the wet end.
That's right. That comes into what the soil water retention curve looks like there. Yeah. There's just a little buffer for changes.
Yeah, on the dry end, there's just so little water in the ceramic.
Yeah.
Yeah, and so those little changes in temperature can make a big difference. Mm-hmm. So there's resources out there to look at this, and we can share them with you. Just send us an email, and we'll get you some of those resources.
And then finally, it looks like we are close to the end of our time here, so this will be our last question. And this final question asks, we monitor soil moisture using water content. How can we integrate this into a soil moisture release curve?
So this is great. If you're measuring soil moisture, mm-hmm. You're not necessarily going to integrate it into the soil moisture release curve, but you can use a soil moisture release curve to then quantify the changes in water potential for the sites where you're measuring soil moisture.
Take your soil sample from when you installed your water content sensors. You did take a soil sample when you installed water content sensors. Take that sample, do the soil water retention curve on it, and then you have a transfer function to get over to your water potential.
Yeah. As Chambers said, it's always a great idea to take a soil sample when you install sensors. Just that way you can characterize it and understand what's going on down there.
Exactly.
But yeah, if you have the sample to characterize the soil moisture release curve, then you can use some of the different available functions out there. There's the Van Gunington equation. There's Brooks and Corey. There's the Fredlin-Zing equation. There's several options out there that you can then take those values that you get from the soil moisture release curve mm-hmm. and apply the water content readings to that equation and output a water potential.
Yep.
So, yeah.
All right. That's going to wrap it up for us. Thank you again, everybody, for joining us today. We hope that you enjoyed this discussion. Thanks again for all your great questions. And again, if you have any questions we didn't answer, please contact us via our website at metergroup.com. Finally, you can subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. So thanks again, stay safe, and have a great day.